Let's talk a little bit now about Lewis acids. So far, we've been talking about Bronsted Lowry, which I'll just call BL, because Bronsted Lowry takes forever to write out. And I want to use water as an example. So here's our HOH, H2O, as we well know. Let me write that H a little better, just because it bugs me. We got a couple electron lone pairs sitting out here. Now for a Bronsted Lowry acid, that needs something to be able to donate a proton. So if I need this hydrogen to go away, I'm going to end up with an O, like this, with a minus formal charge on it because it has 7 electrons nearby, and an H left over. That's my hydroxide conjugate base. But it can also act as a base. In fact, I don't even need to rewrite it. Let's just take a little snip of it. How about that? Like this. See if I'm any good at it. Put it over here, and we're going to do something opposite. We're going to bring a hydrogen over to it, an H plus proton, over here, and we're going to end up with HOH, like this, and only one lone pair of electrons, and that leaves oxygen only with 5 constituent local electrons, which means it has a +1 formal charge. That's H3O plus hydronium. So water can act as an acid or a base depending on what the concentration of nearby protons would be. And that's important to pay attention to because now we're going to talk about Lewis acids. And that is defined a little bit differently. A Lewis acid is more encompassing because it's not limited to substances that donate and accept protons. That's the Bronsted Lowry method. The Lewis acid is a substance that accepts an electron pair. And a Lewis base is a substance that donates an electron pair. So one way to think of that might be like this. Let's make this go away for a second here. Let's make a Lewis base. So here's a base. Remember, bases make things more minusy. It doesn't matter if you're talking about a Lewis or a Bronsted Lowry. So there's going to be electrons here, and our acid make things more plusy. In that sense, these electrons are going to go to this acid here. So we'll end up forming an acid-base sigma bond like that. So think of the electron cloud. Here's an electron cloud that has a lone pair of electrons, and here's an electron cloud that's empty, and now they're able to bond, and those electrons will pass into this sigma space here between these molecules. That's how Lewis acids and bases work, and we can do that with all kinds of stuff. Let's clear this out and look at an example instead. Okay, how about in the third row here we have magnesium. That's in the second group, so it can form an Mg2+. I'm sure you know that by now. But let's say I have a couple Lewis bases here, B for base, or B for Blake the Tutor. Don't forget to hit me at blakethetutor.com. They can form bonds. This electron cloud here, these electrons are happy to move around, especially to something with a 2+, so maybe I form something like Mg, and we'll have a B here for the base and base over here. And now look what has happened. This magnesium has accepted this lone pair of electrons into its sphere and become a neutral party instead of a 2+ ion, and these bases have become a conjugate acid as a consequence because they have become more plusy. They've lost some of their minusy. I'm trying to keep it a little bit remedial on purpose because we don't want to overcomplicate this. This Lewis acid magnesium did not require a hydrogen like in the Bronsted Lowry group. It doesn't necessarily need to be a proton. If we use the Lewis structure group, we can think of it totally in terms of electrons. This magnesium has accepted electrons from a base, and therefore this magnesium 2+ has acted as a Lewis acid. It has reacted with its nearby compound to make it less negative, and therefore positive, and is therefore acting as an acid. Let's have a little fun now. I'll show you an example. I'm going to show you this boron trifluoride, not base, boron. Don't get confused by that. I'm going to give you an ether, which is an oxygen with a couple of methyl groups on each side of it. It's between 2 carbons. And in fact, I can take these methyl groups away because you should just know they're there, and I can draw it this way for you. And we're going to form an acid-base complex, but I'm going to introduce something technical to you now, so pay attention to this. I'm going to show you a curved arrow from, it's going to go from an electron pair, like this oxygen here, to this boron. The arrow itself shows the direction the electrons are going to move. So you can't do this backwards or just draw a line between them. You want to show them as if you're showing the flow of electrons. So curved arrows show where the electrons are going to move. Notice here that boron, by the way, it's not an octet. Boron's kind of weird. It's only number 3 in this energy level. It's nowhere near the octet side. It's not going to be able to take that many electrons because it only has 5 protons. So it gets kind of funny. Boron always has kind of funny behavior. We'll talk more about that later in the semester. What we want to take away from this is that dimethyl ether here has its electron pair accepted by boron trifluoride, which means this little boron complex acts as a Lewis acid. No proton transferring taking place. There's no hydrogen plus on this diagram for a reason. And it's still an acid because if we look at it in terms of how electrons move and where the plus and minus configuration goes, this accepts a minus from dimethyl ether. Indulge me for a second and let me draw you one last example here. Let's take some hydrochloric acid and I'm going to put it in water. And the water is going to act as a base for the hydrochloric acid because hydrochloric acid is stronger than water is in terms of that. So it's going to end up producing a hydronium ion here like this, which gives oxygen a +1 formal charge. And we're going to get a chlorine ion out of it. But if I use the curved arrow notation, then we can see where it comes from here. We can see that the electrons are going to pop off of this oxygen and bond to this hydrogen, which then pops its sigma bond apart and puts its electrons onto this chlorine, which is how chlorine ends up with an extra electron over here and how oxygen ends up missing one over here. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.